Moving on to alpha decay. Before we begin that, we should talk about what does it mean for something to be radioactive. Well, simply put, it means it's radiating particles. Some things that are radioactive are dangerous to us, other things are not. For example, you are radioactive. You have radioactive isotopes inside your body. I talked about in a previous video about carbon-14 and how it's inside of you. Carbon-14 is radioactive, so naturally you are radioactive. When a radioactive decay happens, it means that object is losing mass. The parent nucleus is losing mass because it has ejected a particle as a result. Now, there are three primary types of decays. The one we're talking about today is alpha decay. There's also beta decay, which is broken up into beta positive and beta negative. And then there's gamma decay. I'm going to stick on focusing on alpha decay, but just some pieces of information for you. The device we use to detect types of decays are called Geiger counters, and Geiger counters are utilizing magnetic fields. The idea is the alpha particle is positively charged with a well-defined mass. The beta particles, beta positive, beta negative, so that's a positive charge or a negative charge, but the mass of the beta particle is significantly less than the alpha particle. And then the gamma decay, gamma particles don't have any charge at all. So what the Geiger counter can do is, as we talked about in the magnetism unit, when a charged particle moves into a magnetic field, it gets deflected. We use the FBI gun law to describe the direction in which it gets deflected. That is how the Geiger counter is determining, is this thing alpha, beta, or gamma? Now, both alpha and beta positive are positives, so how does it tell the difference between that? Well, the alpha particle is tens of thousands of times as massive as the beta positive particle. So that means it inherently has more inertia and will be harder to deflect, and the Geiger counter can be calibrated to pick up on that. It's also worth talking about, well, why doesn't the nucleus rip apart if it's this concentration of protons, which are all positive? The reason is there is another force present, and we call it the strong nuclear force. It is the strongest known natural force to human beings, at least at the moment. And what it does is it allows nucleons to be attracted to each other, far higher level of attraction than gravity. The downside of the strong nuclear force is its range. So for example, if I hop over here, and I'll just draw for you quickly, let's say this is a proton, and here's a neutron, and another proton. Well, we would think these two protons would be repelling each other, and indeed they would be. The strong nuclear force is about at its maximum range between these two protons. So those two protons would still be attracted by the strong nuclear force. Now if I put another proton here, these two guys, there is no strong nuclear force anymore. But between these two, there is a strong nuclear force. So that talks about the kind of limitation of the strong nuclear force in terms of its range. That's part of why, or what the neutron's role is inside of an atom. It's to help create stability because the protons naturally want to blow the atom apart. The focus of this will be on nuclear equations, in particular in the decay. I put up an example of an alpha decay, beta decay, gamma decay, and then a positron, which is a beta positive decay here. You can take a look at, but what I'm going to do is I'm going to go ahead and move on to solving, as you saw here, this particular question. Even if you know how to do this already, still follow along, or at least fast forward to the end, because you're going to need to see how do I punch this into the ChemPad on WebAssign using this notation shown right here. So we have an alpha decay of a polonium-210. So what I'm going to do really quick is pause this video because I need a periodic table up and I don't have that. Okay, so I have the periodic table now. It says an alpha decay of polonium-210 So we go to the periodic table, and I see polonium right here is the 84th element. So that means I will have 210PO84, and since it's an alpha decay, it will yield the alpha particle, which is 4,2 helium. So now I have 4,2 helium. Alpha particle is always 4,2 helium. We'll put a plus here, and we have to see what is left over. Now, the atomic mass will become 206 of the daughter. 210 equals 4 plus 206. The atomic number, 84, equals 2 plus 82. I go back to the periodic table and I see 82 is lead, Pb. So I'll write Pb. This is normally how we do it. WebAssign is going to have you do something a little bit extra, and that is right in here. It's going to have you put in the N value. So what is the N value? The N value is the number of neutrons. So that'll be 210 minus 84. So 210 minus 84 is going to be 126. 4 minus 2 is 2. And 206 minus 82, that is going to be 124. Now the final step is, well, how do I punch this into the ChemPad? So let's pop open WebAssign, and I will go ahead and have the WebAssign right here. So sorry again about the video blipping as I'm trying to work with this interface. So here's how I'm going to take what you see on Paint and how I'm going to put it into the ChemPad. So I'm going to hit Shift 6 because that's going to give me the caret symbol. 210. The underscore symbol is right next to the 0 on your keyboard. You need to hold Shift, you hit that, you get the underscore 84. Now I'm going to type in capital P, O for polonium. I'll do another underscore 126. Then I'm going to do space and hit this yield arrow. And again, caret 4 underscore 2, capital H lowercase e underscore 2, space plus caret 206 underscore 82, capital P lowercase b underscore 124. And I see here 210, 84, PO 126 yields 42 helium 2 plus 206, 82, PB 124. Pop this open and hit submit, make sure it works. And we got a green check.